Hi students, today we are going to be talking about matter and energy, and for these notes you need a double spread of your notebook, so we're going to be using two sides, and you're also going to need your periodic table of elements because we're going to be taking some notes on that as well. Let's start with our title. So I'm going to title this Matter and Energy, and I like to underline my titles and I center them on my page, but you get to do whatever you want. We are going to start these notes with some facts about matter. There are three main ideas. One is that atoms last forever. This means that atoms cannot be created or destroyed. The atoms that are around today are the same atoms that were around 1 million years ago. The next is that mass is a measure of atoms. So anytime we are talking about the mass of something, we are talking about the atoms. And the last of our rules here is that atoms can be bonded together forming molecules. And we're going to spend most of the rest of this time talking about this last idea here, that atoms can be bonded together to form molecules. But before we can do that, we need to actually define what an atom is. Because this is going to be a definition, I am going to put a box around it. Atoms are the single smallest unit of an element. So then, what are elements? Well, let's take a look at your periodic table. Each of the boxes on this periodic table represents a different element. If we were to take a chunk of hydrogen and we were going to split it apart, split it apart, split it apart until we got down to the single smallest thing that was still hydrogen, that would be one atom of hydrogen. And the properties of that atom of hydrogen are going to be different than the properties of, say, an atom of carbon. So the periodic table is arranged in a very specific way. First of all, what we have here is we have the chemical symbol. Often, when we are talking about these different atoms, we're not going to write out hydrogen every time. We're just going to write out H. We're going to write out C instead of carbon. We're going to write out N instead of nitrogen. We are going to abbreviate in order to make it easier. But because there are a lot of elements that start with, say, a C, you can't use C for all of them. So for example, carbon starts with a C, that gets the C. Chlorine gets a Cl. Calcium is Ca. So you are not going to need to memorize these. You'll have a periodic table available, but the main elements that we're going to be looking at are hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. The next thing on here is we have an atomic number. And the atomic number is equal to the number of protons. We are going to come back to that in just a minute, so don't worry about that quite yet. We have the name, and then we have here the atomic mass. And that atomic mass is really just comparing how much does one of these hydrogen atoms weigh in comparison to a boron. This is an atomic mass unit. It's not actually given in grams. It's so small for a single atom that we can't actually measure it. So when you get into chemistry, you'll learn a lot more about how this atomic mass is calculated. But remember that atoms have mass. So different atoms are going to have different masses, and that's because they are made up of more stuff. Mass is a measure of how much stuff there is. So now what I want you to do is I want you to use this information in order to answer some questions. Let's see how you've learned this. How many protons does hydrogen have? How many protons does oxygen have? How many protons does carbon have? Which of these elements has the most mass? Okay, now that we have this information, let's actually draw what an atom is going to look like. So keep your periodic table off to the side, but now let's look at what is an atom. So atoms are made up of a nucleus, and in the nucleus are protons and neutrons. The protons have a positive charge and the neutrons have a neutral charge. Around this nucleus, so this is all together, we have electrons. And I'm going to draw 2 electrons because I had 2 protons. And the electrons just kind of move around the outside of our atom, of our nucleus. So let's add some help in here. So we've got this positively charged thing, that is a proton. It has a positive charge. Then we've got our neutron. And it has a neutral or no charge. And together, these things make up the nucleus. And then over here, we have our electron. And electrons have a negative charge. When I'm looking back at that periodic table, and my atomic number is the number of protons, this atom that I drew here, because it has 2 protons, means that this is a helium atom. If I had drawn 6 protons, then this would be a carbon atom. Okay. We're actually going to go and we're going to keep that periodic table because we're going to write down a few more things on here. The first thing that we want to look at are the electron shells. So in my little diagram, I drew the electrons in this ring, and I put 2 of them in that ring because there were 2 electrons. The first row here, so hydrogen and helium, they can have 2 total electrons in the outer shell. That's how many electrons that outer shell can hold. The next row and the row after it, those can hold 8. And it's 8 each. So these are the number of electrons that the electron shell can hold. And then we also have something called valence electrons. This whole column has 1 valence electron. This whole column has 2 valence electrons. We're then going to skip everything in the middle. This column has 3 valence electrons, 4, 5, 6, 7, and 8. Now our valence electrons are the electrons in the outer shell. So this whole column would have 3 electrons in that outer shell. This whole column is going to have 4 electrons in the outer shell. Keeping this in front of you, let's see how this is going to work. I'm going to look at oxygen. How many total electrons does oxygen have? Well, the reason that I drew 2 electrons here is because there were 2 protons. And in general, the number of protons is equal to the number of electrons. So carbon has the atomic number 6. It has 6 protons. It will have 6 electrons. It cannot have 6 electrons. It could have 7 electrons if it steals one, or if it loses one, it could have 5 electrons. Those are called ions, when you have something that doesn't have an equal number of protons and electrons. We will talk about that. But for right now, let's just assume that we are not talking about ions. So we're talking about equal number of protons and electrons. Oxygen has an atomic number of 8. There are 8 protons, which means there are going to be 8 electrons. So we know we are going to have a nucleus. And I could draw 8 total protons and some neutrons in here, but I'm not going to because I'm lazy. So that's my nucleus. Now around the nucleus, I'm going to need to have 8 electrons. The first electron shell can hold 2 electrons. The second shell can hold 8. The third shell can hold 8. Oxygen is in this second row, which means that it has 2 electron shells. The first shell holds 2, the second shell holds 8. So I'm going to put 2 electrons in the first shell. And then I've got space for 8 electrons in the second shell, but I don't have 8 electrons. I have 8 electrons total, but I've already used 2 of them. So let's go ahead and add in our remaining 6 electrons. 2, 3, 4, 5, 6. Now there are 2 spaces where there could be electrons, but there are not electrons because oxygen just doesn't have that many electrons to split up. So the first electron shell holds 2 electrons. So there are going to be 2 electrons in first shell. There are then going to be 6 electrons in the second shell. And then there are these 2 empty spaces. Those empty spaces are going to be really important when we start talking about bonding. Now, we don't want to have to draw this out every single time. This is really complicated to draw out, especially when we start getting more and more and more electrons and protons and everything. So we actually have something called a Lewis diagram. And a Lewis diagram is a way to show the chemical symbol plus the valence electrons. And this is going to show us what the atoms look like in terms of the important structures in them, the number of electrons, how many open spaces there are, and the chemical symbol so that we know what atom or element we are looking at. So we're going to need to know how to draw these Lewis diagrams. I'm going to start with oxygen because we've already talked about it. Oxygen has 6 valence electrons. I know that because 1, I drew it out, and 2, if I look at my periodic table, I can see that there are 6 valence electrons for the column that oxygen is part of. I'm going to start in the 4 cardinal points. So I'm going to add the first 4 electrons in the first 4 cardinal points: north, east, south, and west. If there are then more electrons, we keep going around. They can be in pairs, no more than that. So this electron is going to get a partner. This electron is going to get a partner. And then we've got these two openings because the electrons could be paired, but they are not. Now, I've drawn these in a different color because Lewis diagrams don't actually include them. We just assume that we all know how Lewis diagrams work and that in that outer shell, you can hold 8 valence electrons. And so because I didn't draw 8, I only drew 6, that means that there are 2 spaces left over. Let's look at hydrogen. Hydrogen has 1 valence electron. That valence electron is in a shell that can hold a total of 2 electrons. So for hydrogen, I only have 1 valence electron. I want you to try this for carbon and nitrogen. So carbon, C, and nitrogen, N. Go ahead and pause, take a minute, draw the Lewis diagrams for these. Let's start with carbon. I find carbon on the periodic table. I see that carbon has 4 of those valence electrons. So starting in my cardinal points, 1, 2, 3, 4. Nitrogen, find it on my periodic table. It's right next to carbon. Nitrogen has 5 electrons in its outer shell. So 1, 2, 3, 4, and then I start doubling them up. 5. If you got that, great job. Go ahead and try phosphorus. So phosphorus is down 1 row, which means that it has 3 electron shells. We're going to have 15 total electrons. We're going to have 2 in the first shell, 8 in the second shell, and then 5 in the outermost shell because the valence electrons are in the outermost shell. It's this shell here, but it's only going to have 5 electrons. What this means is that the Lewis diagram for phosphorus is the same as the Lewis diagram for nitrogen. It just happens that their outer shells have the same number of valence electrons because they are in the same column. Okay, we are going to leave some space down here in case you want to take some of your own notes or give yourself some extra practice. So I am now switching and I'm going over to the top of my next page where we are now going to move on to look at molecules. A molecule definition, so I am putting it in a box. A molecule is when you have 2 or more atoms bonded together. 2 or more atoms bonded together. A really common molecule that you might run into in a class like this or in chemistry is something called methane. And methane is a gas and it has a carbon, and that carbon is bonded to 4 hydrogens. What we have here are we now have 2 different things. We have the atoms, such as the hydrogen here, but we now also have introduced bonds. So molecules are made up of atoms and bonds. The atoms, that's the mass. And the bonds, that's going to be energy. So atoms have mass, but when you bond them together, bonds have energy. So molecules are made up of atoms and bonds, so they're made up of mass and energy. In this class, you are going to need to know the difference between an atom and a molecule. So please use your definitions for atom and molecule now in order to determine if these 9 things are atoms or molecules. Good. Now back to our notes. When you bond atoms together, there are 2 types of bond. The first type of bond, and the one that's going to be way more common in this class, is called a covalent bond. In covalent bonds, electrons are shared. This is going to mean that the molecule is stable. And that's because all outer shells of electrons are full. So here's how this works. Let's look at a molecule like water. Water is H2O. What this means is that there are 2 hydrogen and 1 oxygen in every molecule of water. So I'm going to draw a Lewis diagram. I always am going to start with the oxygen. Oxygen, its Lewis diagram, looks like this. It has 6 electrons in the outer shell. That outer shell is not full. Oxygen like this does not exist. You do not go out in nature and find 1 oxygen atom just floating around. And that is because oxygen, like all atoms, they do not like it if their outer shell of electrons is not full. They want that outer shell to be full. In order to do this, they're going to need to share some electrons with some other atoms. In this case, 2 hydrogens. If we remember from our notes on the previous page, hydrogen has 1 electron in its outer shell, but it only needs 2. So what I'm going to do is I'm going to put a hydrogen next to each of those open electrons for oxygen, and then 2 electrons that are shared is equal to a bond. So when they are shared, that creates a bond. What that means is that oxygen now has its outer shell of electrons full. It has 8 possible electrons in that outer shell. It has 2, 4, 6, 8. Shared ones count. Hydrogen, its outer shell is also full because it can have 2 electrons in its outer shell. Because it's in the first row, it can only have 2 electrons total in that outer shell. Because it has this bond, it is sharing those 2 electrons. Its outer shell is also full. So this whole molecule now is stable because everything has full outer shells of electrons. Because oxygen has 2 spaces in its Lewis diagram, that tells you that it is going to form 2 bonds. Let's look at carbon dioxide. Carbon dioxide, CO2. So there is 1 carbon, 2 oxygen, that's what that little 2 means, in this molecule. This time I'm going to start with carbon because carbon has more openings in its Lewis diagram. So I'm going to start by drawing my carbon. Carbon has 4 valence electrons. What this means is that it needs to form 4 bonds. It's not bonded to 4 different things. It's bonded to 2 different things. It's bonded to oxygen. So I'm going to put an oxygen on this side. And I'm going to put an oxygen on this side. Now you'll notice that I've made my Lewis diagrams for oxygen a little bit different than I'd done in the past. What I'm doing is I'm making it so that the open spaces, like the electrons that are by themselves, those are close to an electron that is going to be in that share or in that bond. So because I've got 2 electrons here, I can create a bond, bonding together carbon and oxygen. And then I'm going to create a bond here, bonding together carbon and oxygen. But carbon's outer shell of electrons is not full, and oxygen's outer shell of electrons is not full. So what I'm going to do is I'm going to take 1 electron from oxygen and 1 electron from carbon, and I'm going to share those in a bond. This is what we call a double bond, because there are 2 bonds. Then I'm going to take the other electron from carbon and 1 from oxygen. I had 1 here and 1 here, so that's going to create a bond between these 2 atoms, creating another double bond. So this is what the structure looks like when we have a molecule of carbon dioxide. I want you to try this for nitrogen. Nitrogen is N2, meaning that we're going to have 2 nitrogens bonded together. So start by drawing your Lewis diagrams for your nitrogens next to each other. Okay, hopefully you drew something that looks like this. Now it's time to start actually bonding these together. So I'm going to take one electron from each, create a bond, one electron from each, create a bond, one electron from each, create a bond. This is a triple bond because we have 3 bonds now. And let's check to make sure that these are actually put together properly. So nitrogen is in the second row, which means that nitrogen can have 8 electrons in its outer shell. Each bond is worth 2, so I've got 2, 4, 6, 8. This one also has 2, 4, 6, 8. That means that this is now a nice, stable molecule. That's for covalent bonds. In ionic bonds, instead of sharing electrons, electrons are stolen. Making ions. So I mentioned briefly earlier that if you don't have an equal number of protons and electrons, that you have an ion. So let's look at how this works for table salt. So table salt is NaCl. I'm going to start with my Lewis diagram for Na. Na is located right here. Na has 1 electron. I put that one there because I know that I'm going to be trying to bond it to a Cl. So I know I'm going to try and put a bond in between these two things. Now Cl is here, which means it has 7 electrons in its outer shell. I'm going to put 2, 3, 4, 5, 6, 7. Now, if this was a covalent bond, I would put a bond right here. But the reason that this doesn't happen is because then sodium, Na, would have 2 electrons in its outer shell. Sodium can have 8 electrons in its outer shell. So that doesn't actually make sodium happy. It makes it more unhappy because now it has 2 electrons in its outer shell. So instead what happens is instead of sharing this electron, chlorine, it's going to take it away. What that means is now Na has lost the 1 electron that was in this outer shell, but it still has all of the electrons that were in the outer shell below it. So it still has 8 electrons in its outer shell. It's just 1 shell down. I'm not going to draw all of those because the electron is still in the world. It just got moved over. So the way that we represent this is we put brackets around our atoms, and then we're going to put the charge that is bonding these together. Na, sodium, lost an electron. If it started out with an even number of protons and electrons, it now lost an electron, meaning it has more protons than electrons, which means it has more positive charges than negative charges. It has a positive charge. It is a positive ion. Chlorine has now an extra electron. It gained an electron when it stole it. It started with equal numbers of protons and electrons, but now it has an additional electron. Electrons are negative. It's going to have an overall negative charge. The reason that these are bonded together is because opposites attract. Positives like negatives, so they're going to hang out in the same space because they're going to be attracted to each other because positives and negatives attract. In biology, we don't use a lot of ionic bonds, so we're not going to talk about those very much. We're going to really focus on these covalent bonds where those electrons are being shared. Okay, the last thing that we're going to do is we're going to write down some facts about energy. Just like with matter, there are 3 facts about energy. 1, energy cannot be created or destroyed. 2, covalent bonds, the ones that we are going to talk about a lot in this class. Those are chemical energy. And then 3, changing bonds. For example, I could make bonds or I could break bonds. So making or breaking bonds either requires or releases energy. So you either have to put energy in, or when you make or break those bonds, you might get energy out of your reaction. And that energy, if it's in the bonds, it is chemical energy. Okay, those are our notes. You're going to need your periodic table. You're going to need these notes. But in order to kind of go through and make these a little bit easier to see, I'm going to add a little bit of highlighting. The first thing is when I am talking about matter, I'm going to highlight that the same color. So my facts about matter, those are important. So I'm going to add a little bit of highlighting to my facts about matter. Also, atoms are matter. So that definition I'm going to give a little bit of highlighting to because we're talking about matter. Molecules are also talking about matter. So I'm going to highlight that because atoms have mass. So we're talking about that matter. My energy things I'm going to highlight in yellow just to keep those together. So first of all, I've got my facts about energy. I've got 3 facts about energy. And I've got this statement here that bonds are energy. Okay, so when I'm talking specifically about covalent bonds, I am talking about energy. All right, those are our notes. Hopefully you enjoyed this lesson. See you tomorrow.